Hello people, these are the answers to some of your requested questions. Over the last couple of days you've sent me some emails asking me to explain a few questions, and here they are. This is from the chapter review, chapter 6, it's on page 225. So question 2, it said one of the fastest objects ever made on Earth was the Galileo probe, which got up to 50,000 meters per second at one stage when it was approaching Jupiter, and you were asked to calculate the Lorentz factor for it at that speed. Okay, well there's the velocity, and there's c, the speed of light, 3 by 10 to the 8 meters per second. Formula for the Lorentz factor, sub them in, get the answer. Now, the reason that somebody asked me about this one is almost certainly because the answer was incorrect in the back of the book. Right? This is how to do it. Now, there are two ways to do it. This is the long way. This is the slightly more complicated way because you use the big numbers in the formula. Right? As long as you can drive a calculator to get that, giving you that answer, that's fine. But there is a slightly shorter way to do it. It involves doing this. Instead of putting the velocity in meters per second and c in meters per second, just get the velocity as a fraction of c. So just do that fraction. Right? See what that comes to, and that's your v. Right? So v equals this, and that makes c equal to 1. Right? So then you can just use this. Right? It's the same thing, but the numbers are a little bit faster to go through. The denominator of this fraction is always 1, so it just speeds things up a little bit. In some cases, it makes it way easier to do. In this case, that's still a pretty yucky number on the top. Doesn't make any difference though. Still get the same answer. Right? So that's question 2. Next one that was requested was question 9. Question 9 said there were 2 spacecraft. I'm going to draw the situation up here. So here's Earth. 2 spacecraft heading out away from Earth, spacecraft A, spacecraft B. An observer back on Earth at point C is looking at them. Right? Excuse me. And the question says, describe how the crew of A would see the crew of B and the crew of C. Right? Excuse me. So the question says, observer C will see people on A and B moving in slow motion. Observer C doesn't see the spacecraft going away in slow motion. Observer C sees the spacecraft going away at whatever speed they're actually doing. But action on the spacecraft, like ticking clocks, etc., would have been slowed down if you could see it from here. So what are you going to see from there? Right? Now here's the answer. A will see B as being completely normal because they're traveling at the same speed. They're in the same frame of reference. It's an inertial frame of reference. They're not speeding up, they're not slowing down, but they're going at the same velocity as well. So it's just like me standing next to you on the road on Earth, right, in a classroom. Right? We're going at the same speed as well. Earth is carrying us around and everything looks completely normal. So as long as these two are doing the same velocity, they'll look across to each other and nothing will appear different at all. It's as if they're sitting still back on Earth. Right? But if A looks back at C, A will see the action at C happening in slow motion as well, because according to A is standing still and C is retreating backwards at the speed that this thing is actually going forwards. So because there's that relative motion backwards, C relative to A will see C in slow motion, just like C will see A in slow motion. I'll clarify that a little bit later on when I get to another question, question 14 down here. But the answer to question 9 pretty much goes like this. Spacecraft A and B are going at the same velocity. They're in the same frame of reference, so everything's normal. Observer C appears to be moving away from A backwards at point 9C, therefore time appears to be slower at C. Right? I'll give you the overall rule for how all of that time dilation works in a second. Question 13 was the next one that people asked for. This is about a spectator standing next to a pool clock and watching a swimmer who is swimming somehow at a speed of 2.25 by 10 to the 8 meters per second. And you had to find out how much time would have passed on the swimmer's watch if the time on the clock said 1.5 seconds. So you need the Lorentz factor here. And the proper time is the time on the thing that's doing the moving. And that's what we have to find out. So firstly, Lorentz factor, and another little shortcut that you can do. The question said traveling at 2.25 by 10 to the 8 meters per second, and the speed of light is 3 by 10 to the 8 meters per second. You were going to write by 10 to the 8 above and below that line, so you can just cancel them out and pretend they're not even there. If they're the same, just put these numbers in. Again, it just saves you a few more seconds, and it also removes another potential for making an error on a calculator without realizing it. So it's worth doing it the short way. So you get 1.512 for there, throw it into the formula, and you need to find this. You know that it should be less, right? You know that time slows down, clocks move slower on things that are moving relative to you. The swimmer is moving relative to the person on the pool, so you know the answer has to be less. So if you ever forget which one of these is which, right? If the answer ends up being bigger than 1.5, you know you've got them around the wrong way. All right. Question 14. The answer to question 14 is C. Let me read it to you first. 14 says, in the twin paradox explanation, when can you say that the twin that stays at home does age faster than the twin that goes on the journey? Well, the answer is C. The answer is when one of them is accelerating. But I thought I'd just put this overall rule about time dilation in here. Right? This is pretty much the Bible of time dilation here. This is what the Lorentz factor tells you in the formulas, etc. If two people are in the same frame of reference, like two people just standing in a room on Earth, right, or moving together in a bus or in a plane or in a spaceship, but if they're both in the same frame of reference, both traveling at the same velocity, there isn't any time dilation, everything's normal. If two people are in different inertial frames are going at a constant velocity. For example, me standing on Earth, you flying by at a constant fast speed in a spaceship. There is mutual time dilation. And by mutual, I mean I think that time is going slow for you, and you looking at me, you think that time is going slow for me. We both think that the same thing is happening. They can't both be happening, but that's how it appears to both of us. The only time when we agree on what's actually going on is when one of us is accelerating and the other one isn't. So if I'm standing still on Earth and you are accelerating away from me, not just moving past, but if you're accelerating or decelerating, right, I will see time going slower for you. And if you can look at me while you're accelerating or decelerating, you will see time going faster for me. Those two things actually agree with each other. Right? I'll see time going slower for you than for me, and you will see time going slower for you than for me. And we'll both see that I'm aging faster than you, for example. Right? That's the only time that we actually agree that the same thing is happening. When this was happening, the second circumstance, you think I'm going slow and I think you're going slow. They both can't be happening, so it's a little bit of an optical illusion. But this is the only time when the reality is obvious for both of us. Okay. Question 17, there is a star 5 light years away from Earth. Somebody called Raku heads from Earth towards that star at a speed of 0.9 c. And part A says, for those who are watching from Earth, how long will it take to reach that star? Well, it's just going to be normal, right? Because the Earth and that star are in the same frame of reference. They didn't say that the star was traveling towards us or away from us or past us at a great velocity. So the distance from us to the star really does look like 5 light years, and it is, right? And the people who are going there really do look like they're traveling at 0.9 c, and they are. So you just use flat Isaac Newton formulas here, right? Velocity is distance over time. There's no time dilation going on yet. So if you just figure this out, you come to 5.6 years. So it should take, according to Earthlings standing on Earth, it should take them 5.6 years to get there. And according to Earthlings, it will take them 5.6 years to get there. If we watch them in a telescope and monitor their trip, it'll take 5.6 years before they get there. Now, part B is from the pilot's point of view, from the person in the spacecraft's point of view. How long will it take to reach it? Okay. So you're trying to find the proper time here. The proper time is the time that's on board something that's moving. Again, first things first, find the Lorentz factor. It's 2.2942, 0.9c, 1c. That's where I got those two figures from. Throw it into the formula. That's the formula rearranged like this. Pardon me. T0, the proper time, the time on board, is 5.6 divided by 2.2942. And again, if you get confused as to what's what, you knew that this answer had to be less than 5.6. Right? Because as soon as something starts going fast, time goes slower. So it's going to take you 5.6 years to watch 2.44 years go by. That's going slower. All right. Part C. You had to explain this. Explain why is it that although the pilot knew that the star was 5 light years from Earth and that she was going to travel from at 0.9c, it took much less time. Once you get in the spaceship and you start moving, when you look out the window, you get the effect of, pardon me, of distance contraction or length contraction. The length between your spaceship and the star, the destination, right? That length, the length that you're about to travel, contracts. So it looks like suddenly you don't have as far to go. It feels like you're still traveling at the same speed. As long as you're traveling at the same speed as the spacecraft, everything about being in the spacecraft is going to look normal. But the outside world is flying past the window at 0.9c, so it starts to look abnormally short. So every distance you could travel looks shorter, and therefore you end up taking less time to get there, as you'd expect. 18, last one that people asked for. Excuse me. This was the one about taking a photograph of Australia whilst moving at 8 kilometres per second. This is as fast as the International Space Station moves around Earth. It takes about an hour and a half to go around once. And because it's moving, things that are out the window that aren't moving will look a little bit shorter than they really are, right? You'll get the effect of length contraction. So if you look down and see Australia, how much shorter will Australia actually be? Now this is not very fast compared to the speed of light, so there's not much change. You calculate the Lorentz factor and that's what it comes to. 1.0000000000711, right? Almost exactly 1. So you put that into the formula. Proper length is 4,000. And Australia ends up from space looking like it is only that big, barely any difference, right? So Australia appears, subtract that from that, Australia appears that many kilometres shorter. That comes to 2.8 millimetres shorter, so it barely makes any difference at all. All right, for now, that's every question that I've got from you. Keep firing them in. Thanks, guys.